Self-consistency secrets. Transform LLM optimization now. What if the secret to making AI as reliable as human reasoning was hiding in plain sight? Imagine solving puzzles, cracking tough questions, or even tackling everyday decisions with an AI that thinks like you, layer by layer, step by step. Today, we're uncovering a groundbreaking method that takes AI reasoning to a whole new level. Self-consistency decoding. Introduction, a breakthrough for complex thinking. Let's face it, AI has come a long way. But when it comes to multi-step reasoning, even the smartest models sometimes falter. Why? Because their thinking can lack consistency. But what if we could unlock an approach that mimics human problem-solving? Let's dive into how self-consistency decoding is transforming AI from a guesser into a thinker, a future of reliable AI reasoning. Self-consistency decoding isn't just an improvement. It's a step toward human-like AI reasoning. Whether solving math problems, logical puzzles, or real-world challenges, this method elevates AI accuracy and reliability. In AI development, self-consistency improves the reliability and transparency of language models, making them better suited for applications that demand high accuracy and explainability. By leveraging multiple reasoning paths, self-consistency not only enhances the correctness of outputs, but also instills confidence in the results. The problem with greedy decoding. Most AI relies on greedy decoding, choosing the most probable next step every time. It tends to focus on local optima, meaning it may settle on a reasoning path that appears plausible but is not necessarily correct or optimal. Additionally, greedy decoding lacks diversity in reasoning paths. It consistently generates similar responses, ignoring other potential avenues of thought that might lead to the correct answer. Enter self-consistency decoding. Now, picture an AI that thinks like a team of problem solvers. Self-consistency decoding is an innovative strategy designed to address the limitations of code T prompting with greedy decoding. Instead of relying on a single reasoning path, this method samples a diverse set of reasoning paths, allowing the model to explore multiple ways of approaching a problem. The core idea is to aggregate answers from these diverse paths and select the one that appears most consistently across them. The process begins with sampling reasoning paths using probabilistic techniques like temperature sampling, introducing randomness into token selection, or top K sampling, restricting choices to the K most probable tokens. Once these paths are generated, a majority vote among the answers is taken, with the most frequently occurring answer deemed the final output. This method enhances robustness by mirroring human problem-solving behavior, where confidence in an answer increases if it is supported by multiple approaches. This is the visualization extracted from the paper, Why Self-Consistency Works. Think about how you approach a tricky problem. You test ideas, cross-check them, and settle on the best result. Self-consistency mirrors this, using diversity to weed out errors. The effectiveness of self-consistency lies in its ability to simulate the diverse reasoning processes humans often employ. When faced with a challenging problem, people commonly approach it from multiple angles to validate their solution. If different methods converge on the same answer, confidence in its correctness grows. Self-consistency applies this intuition to language models by leveraging diversity in reasoning paths. Incorrect paths, which may arise from model errors or random sampling, are less likely to converge on the same answer as correct ones. By sampling and aggregating, self-consistency ensures that the final answer is robust and less prone to errors. This statistical strength allows the model to filter out inconsistencies and focus on the most reliable solution, significantly improving performance. Extensive experiments have demonstrated the remarkable effectiveness of self-consistency in improving reasoning tasks. For example, on arithmetic reasoning benchmarks like GSM-K, self-consistency outperformed traditional QOT prompting with greedy decoding by a substantial margin, achieving a 17.9% accuracy improvement. Similarly, in common-sense reasoning tasks such as strategy QA, it yielded a 6.4% improvement. The approach was tested across a range of models, including GPT-3 175B, LLM 540B, LaMDA 137B, and UL220B, with larger models showing even greater gains. The findings also revealed that self-consistency outperformed alternative methods like sample and rank, which selects the most probable reasoning path, and beam search, which generates multiple outputs but lacks the diversity needed for robust aggregation. These results highlight the scalability and general applicability of self-consistency across different reasoning benchmarks. Strengths of self-consistency. Self-consistency decoding is a method used in natural language processing to improve the reliability of outputs from large language models, LLMs. Instead of directly using the highest probability response from a single pass of beam search or greedy decoding, self-consistency generates multiple diverse responses by sampling from the model and then aggregates these responses to determine the most consistent or consensus answer. Here are the key strengths of self-consistency decoding: improved reliability and robustness. By leveraging multiple outputs, self-consistency reduces the impact of any single poor or outlier response. The aggregated result is more robust to model imperfections and noise in sampling. Self-consistency captures the probabilistic nature of language by considering diverse possibilities and converging on the most consistent interpretation. This is particularly useful for tasks where multiple plausible answers exist. Alignment with human intuition. Human reasoning often relies on consensus or majority opinion as an indicator of correctness. Self-consistency mirrors this approach by selecting the answer most agreed upon across samples. By considering multiple potential outputs, self-consistency is better at incorporating nuanced understanding and producing results aligned with contextually appropriate reasoning. Mitigation of mode collapse. Self-consistency encourages diverse output generation by sampling from the model's distribution, avoiding over-reliance on a single high-probability sequence. Tasks requiring multi-step reasoning benefit from the diversity of intermediate steps. Self-consistency identifies patterns in reasoning that align with the correct logical path. Enhanced performance in open-ended tasks. Open-ended tasks, such as generating creative responses or solving riddles, benefit from the exploration of diverse possibilities. Self-consistency can identify the most insightful or accurate response through aggregation. In applications like brainstorming or content creation, self-consistency provides richer outputs by synthesizing diverse perspectives. Improved results in reasoning tasks. For tasks like solving math problems or puzzles, self-consistency often improves accuracy because the model generates various reasoning pathways, and the aggregation process identifies the most coherent one. Unlike greedy decoding, which may prematurely fixate on suboptimal reasoning, self-consistency explores a broader set of possibilities before converging. Turing machine complexity analysis. Analyzing the time complexity and space complexity of self-consistency decoding using the framework of a Turing machine involves several considerations. The Turing machine model allows us to assess computational steps and memory usage rigorously. Here's a breakdown. Process overview of self-consistency decoding. Self-consistency decoding involves three main stages. Each of these stages has distinct contributions to time and space complexity. Sampling diverse outputs, generating K outputs by sampling from the model's distribution. Evaluating consistency, analyzing the sampled outputs to determine a consensus response, typically the most frequent or most consistent. Selecting the consensus, outputting the final result based on the evaluation. Time complexity analysis, sampling diverse outputs. This step generates K outputs, where K is the number of sampled responses. Each sample involves a traversal of the model's internal token generation process, which includes number of tokens generated per output, T, the length of each output in tokens, model computation per token, the cost of computing the probability distribution for a single token, where n is the model size, which includes number of parameters, layers, or hidden states. Each token requires processing through the model, typically involving matrix multiplications. The complexity for generating Ka outputs is OTCN. For transformer-based models, CN scales approximately as ON2 to ON3 for attention computations, depending on whether optimizations, e.g., sparse attention, are used. Evaluating consistency. Once K outputs are generated, evaluating consistency involves frequency counting or clustering, counting identical outputs or grouping similar ones. This process depends on the similarity metric used. Comparison across outputs. Comparing K outputs requires pairwise comparisons, which scale as OKL2. For K outputs, each of length T, comparing all pairs, has a complexity of OKLT. Selecting the consensus. The consensus selection step involves determining the most frequent or consistent output, typically via a sorting or clustering operation. Sorting K outputs has a complexity of O-clog K. If clustering or other similarity-based methods are used, the complexity depends on the clustering algorithm, but often ranges between OKL2, hierarchical clustering for example, and O-clog K, centroid-based clustering for example. Combined time complexity. Combining all stages, sampling, OTCN. Evaluating consistency, OKL2T. Consensus selection, O-clog K. The overall time complexity is dominated by the sampling stage if TCN is large, or by the evaluation stage if KX2T grows significantly. Thus, OKTC SCOT, space complexity analysis, sampling diverse outputs. Storing K sampled outputs requires memory proportional to the total number of tokens across all outputs, which is OKT. Additionally, during sampling, the model maintains internal states, which require space proportional to the model size and the sequence length, O and T. Since K outputs are processed sequentially, these states do not accumulate across samples. Evaluating consistency. Storing K outputs for consistency evaluation requires space proportional to OKT. Pairwise comparisons or clustering may require auxiliary space for similar metrics or intermediate data structures. In the worst case, this could add additional OKL2 space. Selecting the consensus. Sorting or clustering algorithms use space proportional to the number of outputs, OK. If clustering requires auxiliary structures, this could increase to OKL2, combined space complexity. The dominant terms in space complexity are from storing K outputs and the model's internal states during sampling, OKT1T. For tasks with high K or large model sizes, N, the space complexity is primarily affected by ONT during sampling. Complexity in big O terms. Time complexity, dominated by the sampling term OKTCN for large, N, dominated by the evaluation term OKL2T for large K. Space complexity scales with the output size, KT, and model state size, NT. Practical implications trade-off between K and accuracy. Increasing K improves self-consistency, but significantly increases both time and space complexity. Model size impact. N. Larger models have higher computational costs per token, CN, and greater memory demands for hidden states. Real-time constraints. For real-time systems, K and T must be chosen carefully to balance computational cost and output quality. In practice, efficient hardware and optimizations can mitigate these theoretical bounds, but the fundamental scaling behavior remains. To classify self-consistency decoding into computational classes, we consider its time and space complexity and evaluate it in terms of computational theory. Below is a breakdown of its classification. Classification based on time, complexity polynomial time, P, sampling O, KTC, N, and consistency evaluation, OXi, KLTT, are both bounded by polynomial functions of K, T, and N. Assuming no exponential growth in any parameter, self-consistency decoding belongs to P, the class of problems solvable in polynomial time. Applicability to NP or NP-hard. The consistency evaluation step involves non-polynomial operations, such as clustering with exponential complexity in certain similarity measures. This could theoretically push parts of the problem into NP, non-deterministic polynomial time. However, for practical implementations, consistency evaluation is polynomial. Thus, self-consistency decoding is in P for realistic implementations. Classification based on space complexity. Logarithmic space, Boole, self-consistency decoding does not fit into L because it requires storage for the full outputs OKT and model states ONT. Polynomial space, PS space. Since space usage grows in polynomial rate with KT and N, self-consistency decoding belongs to P-space. It fits into this class because the algorithm uses a finite amount of memory proportional to the input size, model parameters, and token length. Formal classification. Time, complexity, self-consistency. Decoding is solvable in polynomial time, so it is in the class P space complexity. The space required grows in polynomial rate with input parameters, placing it in space. Computational classes and practical implications. The problem is efficiently solvable for practical values of K, T, and N, given sufficient computational resources. Polynomial time complexity ensures scalability, but the degree of the polynomial depends heavily on CAN. Memory usage is more of a practical bottleneck than time complexity, especially for large models EN and long sequences T. Parallelization of sampling and clustering can mitigate real-world space constraints but does not change the theoretical classification. Weaknesses. Self-consistency decoding, while effective in many contexts, has several limitations and weaknesses. These stem from both the inherent nature of the approach and its reliance on the capabilities of the underlying language model. Below are the key limitations. Computational overhead. Self-consistency decoding requires generating multiple diverse outputs from the model, which can be computationally expensive. This can be prohibitive for large-scale models or resource-constrained environments. The need to produce and evaluate multiple outputs makes it significantly slower than standard decoding methods like greedy or beam search. Dependence on model calibration. Self-consistency relies on the model producing a distribution of plausible responses that meaningfully captures the task at hand. Poorly calibrated models can lead to suboptimal or misleading results. If the sampling strategy fails to capture a diverse and representative set of plausible outputs, the aggregation process may reinforce incorrect or incomplete reasoning. Vulnerability to repeated errors. If the model systematically generates incorrect but internally consistent outputs, the aggregation step may incorrectly favor these errors. This can occur when the model's training data includes prevalent but erroneous patterns. For tasks where the correct answer is less common or underrepresented in the model's learned distribution, self-consistency is likely to fail, as the consensus may not align with correctness. Ambiguity in results. While self-consistency can aggregate diverse responses, it may struggle when no single correct or consistent answer emerges, leading to uncertainty or arbitrary decisions. When multiple equally plausible answers are generated with similar frequencies, self-consistency offers no clear way to resolve the ambiguity. Lack of ground truth validation. Self-consistency does not validate results against external ground truths. It assumes that internal consistency is a proxy for correctness, which may not always hold, especially in tasks requiring external factual knowledge. For tasks involving factual accuracy, like knowledge retrieval or data-based reasoning, self-consistency decoding may propagate errors if the model's internal knowledge is outdated or incorrect. Sensitivity to prompt quality. The quality and diversity of generated responses are heavily influenced by the input prompt. Poorly designed prompts can bias the outputs, undermining the effectiveness of self-consistency. If the prompt guides the model toward flawed reasoning, self-consistency cannot compensate, as it works on the same flawed basis. Incompatibility with certain task types. For tasks where exact answers are required, the diverse responses generated by self-consistency can lead to inefficiency or confusion. Tasks that demand strict adherence to deterministic logic may not benefit from self-consistency, as diversity is not inherently valuable in such cases. Computational trade-offs in real-world applications. In large-scale applications, such as real-time systems or high-volume workloads, the computational demands of self-consistency make it less practical compared to faster decoding strategies. Generating and analyzing many outputs can be wasteful, especially if the added diversity does not improve the outcome meaningfully. Summary of trade-offs. While self-consistency decoding improves reliability and robustness in many tasks, it comes at a cost of increased computational complexity, sensitivity to model calibration, and limitations in tasks requiring precise or deterministic outputs. For applications where speed, factual accuracy, or interpretability are paramount, other decoding methods or enhancements may be more appropriate. Alternative way, verifier models. Verifier models are a promising approach to enhancing the logical reasoning capabilities of large language models by introducing a secondary layer of validation. These models or mechanisms act as a checkpoint system, scrutinizing the outputs generated by the primary model to ensure they meet certain criteria for logical consistency factual accuracy, or task-specific correctness. This two-stage architecture leverages the generative power of LLMs while mitigating their tendency to produce errors, particularly in complex or high-stakes applications. At their core, verifier models are designed to identify and correct flaws in the reasoning process or the generated content. While LLMs are excellent at generating plausible-seeming outputs, they often lack rigorous mechanisms to verify the truth or logical coherence of their statements. A verifier model addresses this gap by acting as a quality control system. For instance, after the LLM generates an answer, the verifier checks it against predefined logical rules, ground truth data, or even statistical plausibility metrics. If the output fails validation, the verifier can either flag the error, provide feedback for refinement, or trigger the LLM to regenerate the response. Verifier models can be implemented in various forms, depending on the use case. One common approach is to train a separate neural network specifically for the task of error detection. This network learns to classify outputs as correct, incorrect, or inconsistent based on training data annotated for logical correctness or factual alignment. Another approach involves symbolic or rule-based systems, which are particularly useful in domains requiring strict logical or mathematical consistency. For example, in a mathematical reasoning task, the verifier could compute the result independently and compare it with the LLM's output. Despite their potential, verifier models also come with challenges. The effectiveness of a verifier depends on its ability to outperform the primary model in assessing correctness, which can be difficult if both are trained on similar data distributions. Additionally, training verifiers requires high-quality annotations and a clear definition of correctness, which may vary across tasks or domains. Computational overhead is another consideration, as adding a verification layer increases the complexity and latency of inference. In summary, verifier models are an effective way to bolster the logical reasoning capabilities of LLMs by introducing an additional layer of scrutiny. They enhance robustness, improve interpretability, and provide a safeguard against errors in high-stakes applications. With advances in training techniques and integration strategies, verifier models have the potential to become a standard component in systems requiring reliable AI reasoning. How could an AI with human-like reasoning transform your world? Share your thoughts in the comments, and let's imagine the possibilities together.